Good morning, honors chemistry students. Today I would like to work on solving a new type of problem. Given the skills that you've been learning, to date you've learned how to solve mole-mole relationships, mole-mass relationships, and mass-mass relationships. In honors chemistry, you are going to encounter a variety of different types of problems which you will need to solve using the skills that you've already learned and creatively applying them to a variety of different situations and demands that various problems will present to you or that you will encounter as an honors chemistry student, such as this problem today, which is problem 9 from your stoichiometry homework assignment, which reads as follows. 10,2-fluoride, formerly found in many toothpastes, is formed in this reaction in which 10, solid 10, reacts with hydrofluoric acid to produce 10-fluoride and hydrogen gas. That being said, again, you can read this expression or equation in one of two ways. One atom of 10 reacts with 2 molecules of hydrogen fluoride, which produces 1 formula unit of 10-fluoride and 1 molecule of hydrogen gas. On the other hand, you could read this as 1 mole of 10 atoms reacts with 2 moles of hydrogen fluoride molecules to produce 1 mole of sodium fluoride formula units and 1 mole of hydrogen molecules. You may recognize the form of this reaction in which it is a single replacement reaction in which 10, being a fairly active metal, at least more active than hydrogen, will replace hydrogen in the acid to produce a salt and hydrogen gas. So this is another different kind of single replacement reaction. Notice that 10 goes from an oxidation state of 0 to +2. So we say that 10 is oxidized, and on the other hand, hydrogen goes from +1 to 0, so hydrogen is being alternatively reduced. That's just a quick review of single replacement reactions. So not only is this a single replacement reaction, it can also be referred to as a redox reaction because 10 is being oxidized and hydrogen is being reduced to its elemental form. That being said, with all of that information, you're asked the following question. How many grams of 10-fluoride, which is one of your products, can be made by reacting 7.42 times 10 to the 24th molecules of hydrogen fluoride with 10? So this is a different type of problem than you've encountered so far. So typically here you're given molecules of hydrogen fluoride, which you have to convert to grams of 10-fluoride as a product. The one thing you always need to remember in all of these kind of stoichiometry problems is that all roads go down the mole road. So as you attempt to set this up in the known, unknown, solution style of problem solving, once again, you need to recognize that in your solution, converting from moles of hydrogen fluoride to moles of 10-fluoride is going to be required of you as a skill. So that being said, what pieces of information have we been given in the problem? Well, we've been given a balanced chemical reaction, which is a beautiful thing because that way you don't have to balance it. Secondly, you've been given the fact that you have 7.42 times 10 to the 24th molecules of hydrogen fluoride that's going to be reacting with 10. So you're going to record that in your known section because you know how many molecules of HF you have is equal to 7.42 times 10 to the 24th molecules of HF. Now that seems kind of redundant, but molecules as a unit represent a quantity called molecules. So the quantity and the unit are the same thing. you've been asked to identify how many grams of 10 fluoride. Grams represent a unit of mass, so you've been asked to find how many grams of 10 fluoride. And my problem solving approach, I don't just want you to put the unit, I want you to put the quantity that that unit represents as well. Mass is typically measured in grams. So that being said, you're going to have to go from molecules of HF to grams of 10 fluoride, which seems discrepant. But yet we can still do that because we can take advantage of mole relationships between hydrogen fluoride and 10 fluoride. You may note that now we're counting particles here because you're given particles of hydrogen fluoride, but now you've got to go from molecules of hydrogen fluoride to moles, which means that you need to consider Avogadro's number, because we know that 1 mole of hydrogen fluoride molecules contain 6.02 times 10 to the 23rd molecules of hydrogen fluoride. That once again is Avogadro's number, because we know that 1 mole of anything contains 6.02 times 10 to the 23rd molecules. So the question is, how many molecules of hydrogen fluoride do we have in comparison to Avogadro's number of molecules? It looks like we've got more than Avogadro's number, which means, translation is, we have more than a mole of hydrogen fluoride molecules, because the exponent of 10 to the 24th is 1 power of 10 greater than 10 to the 23rd. So that being said, when you consider your solution, this looks like a complicated problem, but it's actually rather straightforward. You're going to start with molecules of hydrogen fluoride and convert molecules to moles of hydrogen fluoride. How are you going to go from molecules to moles? You're going to take advantage of this relationship with Avogadro's number. Once you get to molecules of hydrogen fluoride, you have to convert to moles of hydrogen fluoride, you have to convert to moles of 10 fluoride. So we have moles of 10 fluoride. So we're going to go from moles of hydrogen fluoride to moles of 10 fluoride. We're going to take advantage of the fact that we know 2 moles of hydrogen fluoride are consumed to produce 1 mole of 10 fluoride in the balanced chemical equation. That's what we affectionately refer to as the stoichiometric ratio. And then we're going to convert moles of 10 fluoride into grams of 10 fluoride. And we're going to do that using the gram formula mass of 10 fluoride. So we still need to know one quantity, which would be our gram formula mass of 10 fluoride in grams. So we have to actually calculate that. So I'm going to break out the TI-84 graphing calculator, and let's take a look at what the gram formula mass of 10 fluoride might be. When you look up 10 on the periodic table, it has an atomic number of 50, and it has an atomic mass of 118.71. Plus, you know that you have 2 moles of fluorine, and each mole of fluorine has an atomic mass of about 19. So we'll say 2 times 18.998403. And if you press enter, you get a value of 156.706806. I think that we'll limit this to 2 decimal places because of 10, the atomic weight of 10, so our value will be 156.71. So let's go ahead and record this as 156.71 grams of tin fluoride per mole of tin fluoride. Now we have a bridge to go from moles of tin fluoride to grams of tin fluoride. And the solution to this problem should actually be rather straightforward and drop out rather nicely. So first, we're going to calculate the grams of tin fluoride produced, because tin fluoride is a product. I like to give simple statements like this to graders because it tells the grader what quantity and what unit you're actually looking for. So we're actually looking for mass in grams of tin fluoride. We're going to take this unknown statement right here and repackage it down in the solution. So we're going to tell the grader we're looking for mass of tin fluoride and some units of grams of tin fluoride. And we're going to separate that statement from the rest of your solution. You're going to start with what you've been given in the problem. What you've been given is that you have 7.42 times 10 to the 24th molecules of hydrogen fluoride. Now, that being said, we don't want molecules, we want moles of hydrogen fluoride. So we know that each mole of hydrogen fluoride has a given number of molecules, which is Avogadro's number, 6.02 times 10 to the 23rd molecules of hydrogen fluoride. Once again, molecules drops out, cancels out, and now we're to moles of hydrogen fluoride. But we want to get to moles of tin fluoride using the stoichiometric ratio. So keeping in mind that whatever unit you want to get rid of, you put in the denominator, and whatever unit you want to achieve, you put in the numerator. We want to get rid of moles of hydrogen fluoride, so we know in the stoichiometric ratio, 2 moles of hydrogen fluoride are consumed to produce 1 mole of tin fluoride, formula units. So once again, moles of hydrogen fluoride cancels, and now we are to moles of tin fluoride. But ultimately, we want to convert moles of tin fluoride to grams of tin fluoride using the gram formula mass. So we want to know how many grams are in a mole of tin fluoride. And fortunately, we've included that in our known section because that's something we need to know to solve the problem. So we have 156.71 grams of tin fluoride in a mole of tin fluoride. Moles cancel out, and we should be left with grams of tin fluoride. We don't quite have enough room over here on the side, so I'm going to drop my equal sign down just a little bit so we have a little bit more room. You see that we have just a little bit more than 1 mole of Avogadro's number of molecules. And we're going to be multiplying that product by, or quotient, however you want to look at it, by 1/2, which is going to be about half of that value. So what I'm thinking is the mass of tin fluoride we get will actually be about half of 156.71, maybe a little bit more than half. So let's see how this goes. So I'm going to take out my handy dandy TI-84 calculator, which I hope you can see on the video. And we're going to enter 7.42 second EE 24. And we're going to multiply that by 156.71 and divide that by 6.022 times 10 to the 23rd times 2. So we're going to have 6.02 to the 23rd times, I tell you what, I got to be careful with my parentheses here, times 2. I'm a little bit concerned about the order of operations here, so I'm going to go ahead and insert a second parentheses just to make certain that everything works out as planned. Whoop, and we get a go-to error. I think I put in a, look at that, the wrong symbol. So I have to put in a parentheses. Now we should go forward. Wow, that's a pretty big number. I may have miscalculated just a little bit, but let's record this number anyway. Got to rethink my answer, 965.77 grams of tin fluoride. Now, when you think about that value, we have 3 sig figs in our first measurement here because the decimal point is present. So we're going to come from the Pacific side and go through all the zeros till we get to the first non-zero digit. Every digit thereafter should be significant. The 7, the 4, and the 2 are significant. So we should have 3 sig figs in our answer. So I'm thinking we need to drop this 7 and round the 5 to a 6. So our final answer should be 966 grams of tin fluoride. I think what I'd like to do is just to rerun that calculation just one more time to make certain that we've got it correct. So we've got 7.42 second EE, always good to double check yourself, times 156.71, enter. We'll do it this way. Divided by, I'm just going to put the 2 out first to multiply 2 times 6.02 times 10 to the 23rd. Bam, we get the same answer. So I'm reasonably confident that this is our answer of tin fluoride. Sometimes your guesstimations and estimations can be off, but at least it's good to kind of think through the mathematics of what you're doing. That being said, this is an illustrative example of how you deal with many different quantities in chemistry. You don't always deal with moles and grams. Sometimes you deal with particles. And anytime a problem introduces particles, as in molecules, you can employ Avogadro's number to evaluate how many moles are in those molecules of hydrogen fluoride. And that being said, that allows you to go from molecules of hydrogen fluoride to moles of hydrogen fluoride using Avogadro's number, to convert from moles of reactant to moles of product. You use the stoichiometric ratio of 1 to 2, or 2 moles of hydrogen fluoride are consumed to produce 1 mole of tin fluoride. And finally, to convert from moles of tin fluoride to grams of tin fluoride, we employ the gram formula mass of tin fluoride, which allows us to go from moles to grams. And as always, molar masses are the bridge between moles and grams. And with that, that's how you solve this type of stoichiometric problem.